All right, good afternoon, everybody. Let's get started. Hopefully we'll get out of here before the snow really starts. So, a couple things. If you didn't see our Piazza post, based on your responses to the survey, we've decided to only print some handouts out. So we're only printing about 50 copies per lecture. So if you said you wanted, online ones, then please don't take them. Although today's handouts, both online and the printed ones, are a little messed up. I'll fix them right after lecture. So all the slides that come after the slide that says thank you, please ignore. And I guess that's it for now. All right, so let's get started. So today we're going to continue our discussion of how do we write assembly language and start to talk about how we can go about methodically translating higher level programming languages into assembly. And we're going to actually get into how do we go about dealing with procedures this time. Okay, so first, just a very quick recap of what we know so far. So we've learned so far that there's several different types of instructions in our RISC-V instruction set architecture. So we've got our computational instructions, and those are basically our ALU operations. And we have two types of those. We have register-register operations, which basically take both of their source operands and registers and then produce the response and store that into another register. And we have register immediate, which take a single register as an operand plus a constant, execute the operation, and then store the result in a register once again. Then we have control flow instructions. We have two types of control flow instructions. We have unconditional ones where we're always taking the jump to the new location in order to change the order in which we're executing instructions. And these are the JAL and JALR instructions. And today we're going to actually understand what the JAL instruction is all about, which stands for jump and link. And then the other types of control flow instructions are our conditional branches, where we do some kind of comparison, and based on that comparison, we decide whether or not to take the branch. And then finally, we have our load and stores, which are the instructions that we use in order to transfer information back and forth between our memory and our registers. Now, in addition to the basic instructions provided by the RISC-V ISA, we also have a whole bunch of pseudo instructions, which are basically just aliases to other instructions, which make it easier for us to write our assembly programs. And so, as far as your assembly programs are concerned, you can treat the pseudo instructions as if they're plain RISC-V instructions that are available to you. Okay, so there's one instruction that we didn't yet talk about, and so we're going to introduce it today. So we saw this idea of the fact that we could do ALU computations with a constant, right? So if I want to do something like A equals B plus 3, then that would simply translate into a register immediate instruction, where if x1 is holding A and x2 is holding B, then I would simply do add I of x2 plus 3 and store the result of that into x1. Okay, well, so that's great, but we talked about the fact that the constant that I can include in this instruction is limited in size. Okay, I can only store a constant that's up to 12 bits wide. So suppose, that I asked you to do the same thing, but this time with this really long constant. How am I going to go about getting this long constant into the register? Any ideas? Yeah? Yeah, that's actually precisely what we do. And so to make that a little bit easier, what the RISC-V provides for us is one more instruction, which is called load upper immediate. And so what this does is it basically allows you to load constants into the upper portion of your 32 bits. And because it doesn't need too many bits for encoding that instruction, you actually can specify a 20-bit constant. So let's take a look at what that looks like. So specifically, the way that we would specify this is using a pseudo instruction, which is, in order to make it just a single instruction, we could say load immediate and then some large value. So if I say load immediate and then this large value, there isn't actually a single RISC-V instruction that corresponds to that. Instead, it gets translated into 2 instructions. So what's actually happening behind the scenes is at first it's calling this load upper immediate instruction, which is going to take the top portion of my large constant, which is this hexadecimal 1, 2, 3, and it's going to append to it, whoops, sorry, wrong way. It's going to append to it 12 zeros. Okay, and so you're seeing already that I'm starting to produce, in this using this methodology, a very large constant, and then after I've gotten a big constant into my register, then I can add my small constant using my add I instruction, and so then I can add the lower 12 bits of my long constant in order to end up with my long 0x 1, 2, 3, 4, 5, 6 instruction, okay? So I just wanted to present a couple things. So first of all, that load upper immediate instruction. Second is this load immediate pseudo instruction, which we use a lot. So we can also use this load immediate pseudo instruction if I just want to load a small constant. In that case, it gets translated into a single RISC-V instruction like this add I here, okay? And so as far as your usage in your assembly programs, you can always just say load immediate and some constant. That constant can be large or small, and it'll get translated into the correct set of instructions based on the size of your constant. All right, so today we're going to go through and make use of these instructions in order to have a methodical way of translating our high-level language into our assembly language. So we've seen already how to compile, basic expressions. And so let's quickly, go through an example of what I would need to do in order to do the translation from, this set of equations written in C to my assembly. Okay, so the first thing that I need to do is I need to assign my variables to some registers. And so in this example, we're going to assign X to X10, Y to register X11, and Z to register X12. Okay, and then I'm going to take this complicated operation, and as we mentioned, we're going to split it up into simpler operations that can be expressed as 2 source operands and 1 destination operand. Right, so we're going to start off with my X plus 3, and I know how to do that. That's an add I instruction. Now I'm going to go and I'm going to do the Y plus this large constant, and we just learned how to do that. We're going to use a load immediate instruction in order to load that large constant into some temporary register. And now I can add that to my value of Y that lived in X11 already. And we proceed in this manner. And so next, I'm going to take the OR of those 2 first expressions that I produced, and I'm going to store that as my new value of Y, so that overwrites into X11 what I had there before. And then I have my second expression where I have to start off by first doing this multiply by 4. Now, in our version of the RISC-V, we don't actually have a multiply instruction. So how can I implement a multiply by 4 without without a multiply instruction? Yeah. Exactly. And so the way that that gets translated is I do a shift logical left immediate by 2 positions of the value X. And then finally, I do an exclusive OR with Y, and I produce my result and put it into register X12, which holds my Z variable. Okay? At this point, hopefully everybody follows that pretty well. Any questions about that? Yes?
I think I missed this, but in the load immediate, why do we need the load immediate rather than just using add immediate?
Because the constant is very large. And so the add immediate instruction can only support a constant that's up to 12 bits wide. And so that would be, you know, the largest positive number would be in hexadecimal 0x7ff, and this number is larger than that. Okay, any other questions? Yeah?
Can you explain before and next door? What 9 was what would Y take on depending on what comes out?
Yes, so exclusive OR is basically, and we're going to, I apologize for mentioning something that we haven't yet covered. We're going to get to that as we start to learn about our basic gates. But an exclusive OR is basically, I need to find some chalk. It's similar to an OR, except that it only produces a 1 if only one of your two inputs is a 1 and the other is a 0. So if my two inputs are one of these 4 cases, an exclusive OR is going to produce 0 if both inputs are 0, 0 if both inputs are 1, and these two cases where I have a single 1 and a single 0, those produce a 1. Okay? And we're going to see a lot more of that in the coming weeks. Okay, so let's move on to compiling conditionals. All right, and so what we do here is we're basically going to give you a recipe for how you can go about translating your high-level if statements into your assembly language. And then you're going to find that sometimes, you know, you can make your code a little bit shorter by going, making a few optimizations to this, you know, this exact recipe. But let's just see what the recipe looks like. So suppose that I have, you know, in my C code, if expression, then the body of my if. I can translate that into the following. I'm basically going to compile this expression, which I need to check in order to determine if I'm executing my if or not, and I'm storing it into some register. And then I'm going to run the instruction BEQZ on that register. And if it's, what this is checking is it's saying, is this register equal to 0? If it is, that means that I don't want to execute my if condition, and so I'm going to jump to the label end if, which is going to skip the code associated with the if statement. Okay? And so a quick example here, basically, let's say I have x in x10, y in x11. I'm going to create an expression that's going to check, is x less than y? And I can use my set less than instruction in order to do that. And so this set less than instruction checks, is x less than y? If it is, then set x12 to 1, otherwise set it to 0. And now I can go ahead and check whether or not x12 is 0 or 1, and based on that, decide if I branch to my end if, or if I actually execute my subtract instruction, okay? And now, you might say, well, you know, I can think of a slightly smarter way to do this. So can anybody tell me how I could have done this with fewer instructions? Instead of using the set less than, what instruction could I have used? Yes? Exactly. So I could have optimized this slightly by directly checking, you know, is x greater than or equal to y? If it is, then I'm not executing my if statement. But if I follow the recipe, I will definitely get correct code. Okay? All right, and so we move on from there to if then else, and this looks very similar. And so once again, the if portion looks the same, where I'm compiling my expression into a register, and I'm saying if that register is equal to 0, then I don't execute my if, so I branch to the else. If I do want to execute the if, then I have the compiled portion of that if statement, and now there's one, you know, extra instruction that I need to add here, which is jump end if. What is that jump end if doing? Yep. It's skipping the else, right? So once I do the if statement, I don't want to do the else, so I have to skip it beyond it. And then if I had jumped to the else in the first place, then I will execute the code associated with the else. Okay, how about loops? Well, we can also implement loops with branches. These are branches that would basically branch backwards. Okay, so let's take a look at how that would work. So suppose I had, some C code that was a while loop, which said, while this expression is true, execute this body of the while loop. So I could compile this expression again into a register. Once again, I could say, if that register is equal to 0, that means I don't want to execute my while loop, so I jump to end while. If it's not 0, then I do want to execute it, and so I have the code associated with the body of the while. And then I, at the very end, have this unconditional jump to while in order to repeat my while statement, which once again is going to check for the condition and determine whether to execute it again. Now, here's another situation where we can slightly optimize our code. And the way that we can do that is to move the code that checks for the condition of whether or not you're going to execute your loop to be at the bottom. Okay, and so the way that this would work is initially, before my loop code, I have a single jump to this comparison code in order to execute the checking whether I'm executing the first instance of this loop. Okay, and then there, it's basically the reverse of what we said before. So in this case, I'm going to put the value of the expression into some register. And when do I want to actually execute the loop? I want to execute it when that expression is true. And so I check if it's not equal to 0, meaning it's true, then I go ahead and I execute the code associated with loop. Okay? Any questions about that? Yeah.
How is that fewer instructions?
It's not fewer instructions in terms of the number of instructions, but in terms of the execution, you're not doing both this branch and this jump. So you're not doing two control flow instructions per iteration of the loop. Instead, I just have one branch every time through the loop. Very good question. Any other questions? All right, great. Okay, so this basically, gets us to the point where we're now getting ready to start thinking about more complicated code, okay? So first, let's take a look at an example where we're putting all of this together. And so, here I have some high-level C code where that's got a while loop, and inside it, it's got an if and else statement. And so I can go and follow my exact recipe in order to translate this, right? So the first thing I do is I associate some registers, specifically here x10 and x11, with my variables. I then put the recipe for my while loop to replace this while x not equal to y. And so what do I have to do? I first jump to compare. This checks, is x not equal to y? If it is, jump to loop and go ahead and execute that while. All right? Now I'm going to replace the contents, the body of the while. Okay? And so my while is an if-then-else statement, which also we know how to do at this point. And so the first thing I'm going to do is I'm going to check, is x less than or equal to y? If it is, then I want to execute my else. Otherwise, I want to execute the if, and once I'm done with the if, I jump to end if in order to skip the else portion of my code. Okay? So all follows what we've seen so far. All right, well, it turns out that this particular piece of code is actually the guts of a, very useful procedure called GCD, or greatest common divisor. And you can imagine that you might want to use this code over and over, right? And so just like in our high-level programming languages, we want to abstract functionality into procedures so that we can reuse those procedures and also not make the main function have to worry about how that procedure is implemented. We're going to do exactly the same thing here. So what do we need in order to support procedures in assembly? So first, let's think about, what is relevant for procedures in our high-level language. Okay, so here's my procedure. You'll notice that the while statement is exactly what we just translated, but now there's a few more pieces of code that we have to deal with. Okay, so the first thing is that I have to give my procedure a name. okay? And so it has what we call an entry point. And basically the way I execute any procedure is if I'm calling GCD, I'm always going to go to the beginning of the code associated with GCD and execute it all the way through with potentially some control flow instructions within there. But basically I'm always starting in this exact same spot regardless of who called GCD. Okay, what about parameters? So in order to support procedures, we have to have a way of, passing in some parameters sometimes, right? So we're gonna have to think about how are we gonna do that in our assembly language. In addition here, we have some local storage, right? And so it might not be sufficient to just use our registers in the implementation of our procedure. And so we might have to have some dedicated memory space to hold some of our local variables. And finally, we have an exit point from our procedure where we give control back to whoever called this procedure in the first place, and we can either return a return value or not, depending on the procedure. Okay, so as we all know, procedures are basically a great form of abstraction, and they allow for code reuse. And so here we just see a very quick example of this, where suppose that I wanted to write a coprimes function. Anybody know what a coprimes is? Yeah.
Two numbers are coprime if their greatest common divisor is 1.
Exactly. Okay, so how can I implement this? I can make use of my GCD function that already exists, right? So what I'm going to do is I have two numbers, and I'm going to call GCD on those two numbers. And if the GCD of those two numbers is 1, then that means, excuse me, that they are coprimes. So if I was to run this, on 5 and 10, well, 10 is divisible by 5, and so those are not coprimes, whereas 9 and 10 are. All right, so let's start thinking about some of the details of these problems that came up and ideas that we need to resolve in order to actually implement our procedures in assembly. So the first thing is that we need to have a way of transferring, specifying our arguments as well as our return values, okay? And so the way that we're going to do that is we're going to use, let's say, some register. And I have this problem, which is that I don't have a different set of registers for my procedure than I have for my main program, right? So you might say, well, okay, let's say that the way I'm going to do it is that the main program gets, registers 0 through 16, and your procedure gets 17 through 31, and I figure out some way that's going to work for them to, not step on each other's toes. Well, clearly you can see that, even if I have such a convention, it's going to very quickly fall apart if I have, more procedures where I have to divide my register space into more than 2, and how do we go about doing that? So that's not going to work, right? So instead, what we want is we want to have a methodology or an agreement between the caller and the callee that is independent of what the procedure is going to do with those registers, okay? And so keep that in mind, and we'll get back to that. So what we're going to do in order to satisfy that is that we're going to follow a convention where either the person making the procedure call is responsible for saving a register, or the procedure call itself is responsible for saving the register, and which one of those it is going to depend on the kind of register that we're talking about. Okay, now there are a couple other issues other than, making sure that we don't overwrite each other's registers that we need to think about when we're implementing procedures. So in order to pass the arguments to the procedure that we're calling, we can follow a convention that we simply do this through registers. And we're going to see in just a moment that basically in RISC-V we have a certain set of dedicated registers which are specifically for passing arguments, and we also have dedicated registers which are for passing return values. And so there's this contract between the caller and the callee as to how they transfer that information between each other using specific registers. Okay, well, there's a couple other things we have to worry about, which is, you know, my procedure, it can be called from multiple different places, right? So when I finish executing my procedure, I have to somehow go back to the code that called me. So let's think a little bit about, you know, what that means, right? So suppose I have this procedure called sum, and I have my main code up here where I have multiple calls to this procedure sum, all right? Well, it's easy to, you know, to transfer control to this procedure. We know how to do that in assembly. I can just do an unconditional jump to the label sum, and that will start executing the code that's at label sum, which corresponds to my procedure. But, you know, what happens when I'm done with sum? I somehow have to get back to whoever it was that called me, right? And so with just what we've done so far, we don't have enough information to be able to actually continue executing our code where we left off. And so this leads in to our instruction that we have been, you know, holding off on explaining, which is the jump and link instruction. So specifically what has to happen is that when you make a call to a procedure, you have to save the return address of whoever it is that made this call, okay? So how do we save this return address? We use this jump and link instruction where this register labeled RA is the register that we use in order to save our return address. And then the label is the label of the procedure that we're jumping to. So let's take a close look at what happens if I run this jump and link instruction. So we have a convention of using RA, which stands for return address, in order to store our actual return address. Okay, so the first thing that's going to happen is that when I execute a jump and link instruction, if my jump and link instruction is at, I just put a random label here called procedure call, which let's say corresponds to address 0x100 in my memory, then what it's going to store into RA is the address of the instruction that immediately follows this call to my procedure, okay? So if my jump and link instruction is at address 0x100, then what's going to go into RA is 0x104, okay? And so now I'm going to go ahead and jump, you know, to the procedure. I'm going to execute that code, and then at the end, now I know where I need to jump back to. So I just jump back to RA, and that's going to take me back to the code that called the procedure in the first place. So let's just actually take a look, you know, at the example that we were seeing before and see, you know, how this works for us this time. So specifically, you know, if I have two calls to this procedure sum, one of them is at address 0x100 and the other is at 0x678, the first time that I call sum, what's going to go into RA? It's going to be the return address of the instruction that's at address 0x100. So 0x104. So when I finish executing sum the first time, I'm going to jump to address 0x104, which is going to bring me back to immediately after that first jump and link instruction, right? So I then continue executing my code, and now I reach another jump and link instruction, and this time what's going to get stored into my return address is 0x67C, which is 4 more than 0x678, okay? And so once again, I can go and I can execute the exact same code that I executed before, except that now when I say jump to RA, it has a different meaning and it takes me back to another place, Okay? So we've solved this problem of how do we go back to the correct position in the code that called the procedure in the first place. Okay, there's still a couple more issues we need to think about before we, have solved our handling procedures. So the next complication is the following. Suppose that I have, procedure A calling procedure B, and then procedure B calls procedure C. I said that, what I'm going to do is I'm going to store the return address in register A, in this register RA, right? But if I do that, in order, when I call, a procedure from procedure A, I call procedure B, I store something into RA, that's going to tell me the return address for procedure A, right? Now what happens when procedure B calls procedure C? What happens to the value in RA? It gets overwritten, right? So if I have, let's say, I have one procedure which says, jump to B, and another procedure, so this is procedure A, and another procedure B which says jump to C, right? So here, if this was my address was 0x100, and let's just call this 0x200, here I nicely set, RA equal to 0x104. And then I went and I started executing procedure B. And now I get to another jump instruction. Sorry, this is jump and link. And I'm going to set RA equal to 0x204. Well, at some point I'm going to get to the bottom of my procedure B, and what is it going to say? It's going to say jump to RA. Well, what's RA at this point? It's no longer the 104, which I wanted, which was the return address for procedure A. It's now been overwritten, okay? So the problem is a little more complicated than just saving our return address. We actually have to really keep track of every instantiation of a procedure. You have to keep track of all of its registers, of the return address, and so basically this is going to bring us into a new data structure, which we're going to learn about today. All right, so let's summarize, what are all the things that our procedure needs to know about, and what are we going to want to store in this new data structure? So we talked about input arguments. We talked about using, certain registers for passing our input arguments. We talked about using certain registers for our results. We can use a special register to save our return address. We might also have some local storage in our procedure, like suppose that my procedure is really, really complicated and I can't actually implement everything using just my 32 registers, then you can imagine that I'm going to store some things away into memory in order to free up some of those registers and make them available to me. So the question is, as I execute these procedures, where does all of this information live? And so what we're introducing is this concept of what we call an activation record, okay? So all of the information that each instance of the procedure needs is going to get stored together into some location in memory. And specifically, the data structure that we're going to use in order to do this is what's called a stack. A stack, the way that things are stored in a stack is in a last in, first out methodology. Now let's think about why, this makes sense for our procedure calls. So specifically, I have a few instructions that I can execute on a stack. I can push something onto a stack, which means just put something on the top of it. I can pop something from the stack, which means take something off the stack, or I can just look at the top element of the stack. At no point am I going to go really and look too much further from the few elements that are on the top of the stack. So suppose, that I have these procedures, A calling B calling C. What I'm going to want is I'm going to want to have, first some embodiment of all of the registers that are associated with procedure A, which I need to keep track of, like its return address, and I'm going to store that into a chunk of memory by pushing onto my stack. Okay? So now when procedure A goes and it calls procedure B, I'm going to have another chunk of memory that I put onto my stack on top of that. Okay, and so that location in memory doesn't interfere with a chunk that's associated with the original call to procedure A. And similarly, when procedure B calls procedure C, I'm going to create yet another activation record, and I'm going to push that onto my stack. Now, as I start to return from my nested procedures, I no longer need this information that I stored into memory. And so what's going to happen is I'm going to start taking it off of my stack by popping it. And so I'm going to go back to the scenario where I don't have the activation record for C anymore. Now I only have B and A. And then finally, I go back, to where I just have A. Okay? And so this is basically what we're going to do in order to be safe in our procedures. So what does this allow us to do? It allows each of our procedures to basically make use of the entire register space, right? We don't have to do any kind of sharing where, we have to be worried about is some other procedure that might get called later on going to overwrite my registers. And we're going to have conventions of exactly how we go about doing this. All right, so first, let's just take a little bit of a closer look at this stack, which is basically a section of memory, and let's make sure that we understand how it works. So the first thing that we need in order to make use of a stack is a special register, which we call the stack pointer. And the stack pointer is going to point to the top of the stack, okay? And the way that addresses grow as far as the RISC-V stack is concerned, and this is different depending on the instruction set architecture, is that as we push things onto the stack, we're actually going from higher addresses to lower addresses. Okay, so basically, if you do a push onto the stack, it actually decreases the stack pointer. A pop onto the stack, a pop from the stack decreases the stack pointer. Increases the stack pointer. Sorry about that. And then the stack pointer itself is always going to point to the last filled location on the stack. Okay, so the stack pointer in the RISC-V is always pointing to a valid location. All right, so the key about a stack, though, is that our discipline is that we can use the stack anytime. So what does this do for us? It basically kind of gives each procedure an infinite amount of storage, okay? It gives it space to store as many local variables as it wants, to save registers that other procedures might want to use, and so on. But the key is that when you enter a procedure, you received the stack in a particular way. It's your responsibility to always return the stack in exactly the same way. So let's see what that means. So when I call a procedure, what my entry sequence, or the first few lines of my procedure might look like, is I'm going to, put some space, allocate some space on my stack. Let's say, that in this example, I need to store 2 things onto my stack. And so what I would do is I would add -8 to my stack pointer in order to give myself, these 2 spots on my stack. And so before, my stack pointer was pointing over here, and now it's pointing over here. Okay, and so then the next thing that I'm going to do is I'm going to store the registers that I want into these locations that I just created on the stack. So if I say store word RA into 0SP, well, I just made SP point to this top new location, which doesn't have anything stored in it, and so that's going to say RA associated with this register into my stack, allocation 0 off of the new stack pointer. Then, if I have, store word A0, let's say, I'm going to, store this other register, which is called A0, onto my stack. Now, when I finish executing my procedure, I have to do exactly the reverse because we need to make sure to give the stack back in exactly the way we received it. So how do I do that? First, I'm going to restore the registers that I saved. So I'm going to grab the value of RA from location 0 SP, the value of A0 from location, sorry, that should say 4 SP, and then I'm going to increment the stack pointer to go back to its original location. And so when I'm done executing my procedure, I go back to having my stack look exactly the way that it looked before. Okay? Any questions about that? Great. Okay, so now things get, a little bit messy, but hopefully with some practice you'll get used to this. So what we're going to do is we're basically going to define a calling convention, which is going to specify who is responsible for saving things onto the stack depending on what the type of register is. And so specifically, we're going to take our 32 registers that the RISC-V provides us, and we're actually going to divide them into a few categories. So the first category are the types of registers that we've talked about so far today. So we call these the A registers. We have A0 through A7. These are our argument registers. And so we're always going to follow the convention that when I'm executing a procedure, I'm going to put the arguments that I'm passing to that procedure in these registers. So if I have a single argument, it's going to go into A0. If I have two arguments, it'll go into A0, and then the second argument into A1, so that the procedure knows exactly where to find them. Similarly, my return values, by convention, are always going to go, generally we just have one return value, so it's going to go into A0. If I happen to have two return values, I'm going to use A0 and A1. And then we also have this special register RA, which stands for return address, which is where we're going to store the return address for whoever it is that called our procedure. Now, remember that until now, we always talked about our RISC-V registers as being registers X0 through X31. That hasn't changed. All we're doing is actually adding some symbolic names that have meaning to each of these registers. And this table that you're going to see right now is basically going to show you the mapping from the symbolic names to the X registers themselves. Okay? And so first we've got our 8A registers and our RA register. Then we have some two different types of registers. We call them temporaries and saved registers. And so what we mean by temporaries versus saved registers is that how we deal with making use of them in our procedure is going to follow different rules depending on whether it's a temporary register or a saved register. So specifically, as you might imagine from the name, a temporary register is a type of register where you can't assume that when you make a nested procedure call and you return from that nested procedure call that that temporary register still has the value it had before you made the call. Whereas in a saved register, you can make that assumption, okay? And so that's going to dictate how it is that we go about writing and picking specific registers in the implementation of our procedures. And then finally, we have a couple extra special registers. So the stack pointer we talked about already. And we don't really need to talk about the global and thread pointer right now, but those are two additional registers that have specific registers dedicated to them. And then finally, we have the one last register, which is the X0 register, which we've already mentioned is always equal to 0. Okay, and now you'll notice that this column on the right here, I've labeled most things, the ones that I actually need to worry about saving, as either caller-saved or callee-saved. So let's try to understand what that means. So a caller-saved register is a register that's not preserved across function calls. Okay, so what that means is that your callee is allowed to overwrite it. So if it's important for your procedure to make sure that that register does not get overwritten, then it's the caller's responsibility to save it onto the stack before making the procedure call, okay? And so what are examples of these registers? So my argument register, my return address register. All of these are registers where I cannot assume that the procedure that I'm calling is not going to overwrite those values with something else. So if I need those values upon return from the procedure, I need to make sure to save them onto the stack. All right, what about Callee-Saved registers? Callee-Saved registers are preserved across function calls, okay? And so in this case, it's the responsibility of the callee to make sure to save it if it's going to make use of them. And so here's where our S registers come into play, okay? So we're told that these S registers, which are special saved registers, are guaranteed to always have the same value when you return from the procedure call that it had before the procedure call. So that means that within the procedure, if I'm going to go ahead and make use of these S registers, I have to first save them onto the stack before I can modify their values, okay? All right, so let's take a look at, some examples of callee-saved registers versus caller-saved registers. So suppose that I'm trying to implement this function f shown here, where, I've got two input parameters, x and y, and let's say that, I want to use the registers S0 and S1 to store these temporary values that my procedure is going to use. So the body of my procedure would look something like this, right? I'm going to have, my first argument is in A0, right? So that's where x is. And I'm going to add to it the constant 3, so that's this add I A03 instruction. And it's going to store its result into some temporary register, which this particular procedure chose to use S0 for. Okay? Then I'm going to have a load immediate into some other register, S1 specifically, where I'm going to load this big constant. I'm then going to add y to it and store it again in this S register. And finally, I'm going to take the OR of those two temporary registers in order to produce my result, which I'm going to put into A0 because by convention we put the result of the procedure in the A0 register. Okay? So what do I have to do in order to actually make this procedure follow our calling conventions? If it wants to go ahead and make use of these S registers, it has to first put them onto the stack before it overwrites them, okay? So since I'm going to be using two S registers, what I would do is I would allocate 8 bytes onto my stack. I do that by adding -8 to my stack pointer. And then, once I've done that, I can store in one of those two locations my S1 register, and in the other one, my S0 register, okay? I then go ahead and implement the body of my procedure, and once it's done, it's my responsibility to restore these S registers. So how do I restore them? By following exactly the reverse, right? So I'm going to take things off of the stack by loading them from the places that I know that I saved them in my activation record. So I know that S1 is located at an offset of 0 from my current stack pointer. Similarly, S0 is at 4 offset from my stack pointer, and so I can restore those registers. Once I've restored them, I no longer need them on the stack. And so the way that I get rid of them from the stack is by incrementing the stack pointer so that it no longer points to those locations, and now it's pointing just below them, which effectively means that I've taken them off the stack. Okay? Any questions about that? All right, great. So let's take a quick look pictorially at what this looks like. So initially, before I call my procedure, my stack pointer is pointing to the top of my stack, which has, some information associated with it. And what I've done right now is that I've allocated 2 words on my stack in order to save the S0 and the S1 register. I then go ahead and execute my procedure, and when I'm done, I restore my stack to look the way it was before, and in the same time, I'm also restoring my S0 and S1 registers. Okay? So last example is a caller-saved example. Okay? So here, suppose that what my caller wants to do is call this sum routine, and it wants to call it, more than once, all right? So let's say, that it's going to make use of the A0 and, well, it has to make use of the A0 and A1 registers in order to pass the arguments to sum. Right? So the first thing that it's going to do is it's going to load X into A0, which is loading a 1. It's going to load Y into A1, so it loads a 2. And now I'm going to go ahead and I'm going to have the body of my loop. So let's take a look at what happens here before I worry about what happens on the stack. So I'm going to, do a jump and link RA to this sum procedure. And then I'm going to call it once again. And, in between, I might execute some instructions on my stack. Okay? And what does my sum procedure do? My sum procedure just takes these values, A and B, and adds them and returns them in A0. So why is it that, I might need to save these A0 or A1 registers in this particular example? Can anybody see from the code what is going on that makes me need to use the stack? So there's 2 registers that I've chosen to stave onto my stack, okay? So I've allocated 2 words or 8 bytes for before calling this procedure, and that is used in order to save things that the caller is responsible for saving, right? So the types of things that the caller is responsible for saving are the A registers and the RA register, right? And so when might I want to save my A registers? Like in this example, I'm calling sum 2 times, right? And so it needs this variable Y in 2 places, right? So when I use A1 in order to call sum the first time and I return from sum, I can't be guaranteed that A1 still has that value of Y in it, okay? And so in order to, to implement things correctly, what I have to do is I have to store A1 onto my stack, then I call sum. Then when I return from sum may or may not have altered A1, but I'm not going to worry about how sum was implemented because I know that I have the correct value of A1 on my stack. It's stored at location 4SP. Okay, so when I return from that first call to sum, I can go ahead and restore my value of Y by simply doing a load from location 4SP. And that ensures that I have the correct value of Y for my second call to sum, okay? Similarly, I'm also storing a return address. In this particular example, add happens to not call another, nested procedure. And so it's not going to overwrite RA. But I have no way of knowing that from outside of the procedure, okay? And so just for safety, what we always do is we're always going to save our RA register before calling a procedure, and we're going to save any of the A registers that we need to access their value for, and upon return from the procedure, we're going to restore them. All right, so more about this next time, and you're going to get lots of practice in lab. Remember that lab 1 is due on Thursday, and lab 2 is going to be a continued assembly, but we're actually going to start dealing with procedures. Thank you.